Let me make sure the microphones are on. They aren't. It's good that I checked. So now the mics are on. All right, so what's your name anyway? I forget.
Daniel.
Oh, Daniel, okay. So yeah. Homework from group 3. So I don't know. Oh, is it? Maybe it's because of the career fair.
Wrong question. Yeah.
Maybe it's because of the career fair, like Kyle Rojek, like he's and Rojek's usually doing pretty good in McKee. Connor McKee and then Mesh went 10A. No homework this week, but I don't know. Anyway, it'll work out, I guess. So I guess I'd go through a little bit of the homework. All right, so let's see. I'm not sure what I've already gone through a lot down here, right? Or oops, let's mess that up. Yeah. So I kind of went through that last time, right? How to do that. Everyone kind of did it, I think. I guess everyone's over here today, but I don't see anyone from that group. All right. This thing, so there were two ways they got the theta point. One, they like r squared goes as NL squared when it's at the theta point. And otherwise, if it's in a good solvent, it's expanded. So if you plot it against temperature, you can find that point where molecular weight drops out. If you plot R over N or something, and then that's one way. And the other way is it just the second-order coefficient. And they said, where does that go to 0? He got the same answer for that. All right. So anyway, and then I just wanted you to go through the Floyd-Kriegbaum and kind of say something about the that other equation, which I think everyone kind of did. Sometimes people have put they went to question C and then they didn't do the derivation here. Then they stuffed at the end the derivation. I guess you need to put a note in the homework that the thing's at the end or something so I can find it. But they came back and said it's there. So otherwise they lost like 8 points. So, but anyway, I fixed that. That was you, right? That was your group. No? Okay, there's someone. Anyway, figure 6. This is just define the axes and what does C star mean when you reach C star. And then also define the axes from the equation. So people got that and that. Everyone did okay, I think, in this. Any questions on the homework, or hopefully it's all right. We've already gone through it, I think. So I wanted to go through, let's see, get to here, this one. Oh, we're up to like about 100, like 30 something. This business. So let me go to here. Get this expanded. It's up here, right? So anyway, so we got this situation, like the coil. So we have a good solvent, the thing's expanded, beta solvent, it's like that. And then you can get this collapse through biology kind of. And we said, so there's a region where you get that collapse. You have to be below C star, so the coils are independent of each other. If you're above C star or phi star or rho star, then the coils will meet each other and then they'll form a separate phase. Like the denser phase will drop to the bottom. That's normal phase separation.
So how did they find out that the P star?
You can get it. I thought I showed you guys how to get that. Like you can get it from rheology. I mean, you get it from rheology. Like if you measure the viscosity, it's power 1. So the thing's as if when they're isolated, it's like you pull on it. And if you add another car to the train, it's that much more harder to pull it. So the viscosity goes linear. When you get above that, the things are entangled. I mean, that's one way to measure it. You can do neutron scattering and measure the size of the coil. You can directly get the radius of gyration of the coil. And you know the mass of the coil. You can also get that from neutron scattering. The intercept at 0 for low Q gives you the mass of the coil too. So you get the mass and the size from neutron scattering. You can get the ratio of those two. Cube size gives you the C star. Basically, you need to know the mass and the size somehow. So you can get that size from dynamic light scattering too, if you want the hydrodynamic size. And you can do this viscosity measurement to kind of determine it. It's not hard to figure out. Anyway, you can see this is a log scale. So if you're off by a factor of 3, it doesn't matter much. Right. So if you get a ballpark number for that, that's good enough, because it's always a log plot. So so anyway, yeah, so we can get to the theta condition. Oh yeah, the C star. So we're here. So basically you're below C star, you have mostly independent coils floating around. When those go to phase separate, they don't have a partner to meet up with and then form a separate phase. So they just collapse, right? They just collapse like that. So that's kind of a model for like protein folding or something. You can see if you plot the radius of gyration from like light scattering or the dynamic light scattering. So we'll go through that later, but basically the hydrodynamic radius goes through the same kind of transition, right? And then the ratio of those two tells you when the hydrodynamic is larger than the radius of gyration, then you have a 3D object. When it's smaller, it's like it's a fractal object. So basically the ratio of this RG to RH gives you what the thing is, kind of a little bit of what it is. And you can also get the dimension from the intensity versus Q plot. Log I, log Q gives you the dimension of the thing. So you can see that it's 3D. So basically it goes to a 3D object of some kind. So the homework this week's about that, like what kind of 3D object is it? So these are all like things involving one single coil, like one single chain, not like a melt, So it's important to kind of distinguish you're only talking about here. So, I mean, it's a little odd because if you go into your body, you're actually, your body, like your blood is full of proteins and stuff. So you're actually like concentrated in your body. So it's possible like the polymers in your blood, like the proteins are probably like in theta condition because they're concentrated. Like it's not just one protein, but basically if you take all the proteins, the concentration is pretty high. So you're definitely not over here. Yet we're talking about like DNA folding and protein folding. And this process is happening in the dilute region. So the reason is it's like specific interactions and biomolecules that pull it together, like disulfide linkages and hydrophobic, hydrophilic effects, and just different polar effects going on. So basically, you can get a collapse even when you're in concentrated individual molecular collapse. And also in proteins is like chaperone proteins. There's other proteins that guide the folding. So it isn't just happening, just a chain floating around collapsing. It's got all kinds of helpers around. Other proteins are helping it fold the right way. Right. So it's kind of a different, completely, absolutely different process, but the physicists like to take, there's a chicken, how does it walk? And they say, well, let's assume it's a sphere, right? So they always want to go like a simple model to talk about the thing, right? So anyway, so this is a simple model and it's based strictly in this yellow part of the phase diagram. Right? So, and this is the kind of the current approach to this, which was developed basically by some Russian guys. Even though it's pretty close to like the Flory-Krigbaum stuff, but and then if you read the paper this week, they don't mention any Russians at all, which is kind of strange. So like usually if you're talking about coil collapse, you're gonna see a lot of Grossberg and Koklov and some other Russian guys floating around it, because they kind of worked out this thing. So anyway, the paper this week's from a guy from China, and he references a bunch of Chinese people. It's almost like the days of the Cold War, when like the US papers and polymers would all reference like Flory and all the American scientists, and the Russians papers would reference all their scientists, something Falkenstein and a bunch of other guys, you know, like Falkenstein was a Russian Flory. And they did almost the same stuff, you know, so it was kind of funny. So the Chinese, I guess, are kind of getting into that the same thing. You know? But maybe what goes around comes around. But let me hide this thing. Oops. Can't exactly hide it. Maybe I can. There. All right. So we're looking in that region. So this is from this book, Giant Molecules, which is Grossberg wrote. It's supposed to be like a simplified, dumbed down version with a lot of graphics and stuff. It's pretty good to go there. I mean, otherwise it can get pretty complicated. Anyway, so what he does is, so we have this coil expansion factor. So we have this C infinity, which is the coil size divided by the theta size, NL squared versus the step size changes. So that's a short range interaction, like local interaction. And then this thing ends up being LK by L naught. And then Flory defined this coil expansion factor for long range interactions, which looks like the same thing. It's the coil size versus the theta size. But this has to do with the coil expanding, right? So basically this has to do with, so you take the square of R, which would be 3/5, and then the square is 6/5. And this is into the 5/5. So 6/5 minus 5/5 is into the 1/5 for this coil expansion factor. So it's the same thing as the infinity, but it's for long range interactions. It doesn't have the step length in it. Right. So you're kind of measuring the same thing, but this is just considering the coil expansion. Anyway, so Grossberg doesn't use that definition, which is a standard one. He uses this definition. So he says alpha squared, because that way you can say alphas are, right? So he wants to say alphas are, so he just says alphas are. And then you'd get that alpha is into the 1/10, but that might cause a little confusion, you know, in looking at this stuff. But anyway, that's like a preamble to this. Anyway, so this is kind of like a simple just random walk simulation. It shows kind of what the things would look like. He had kind of a short chain, and this is, I think that's from Grossberg's book. And this is a color graphic he had where this is all one chain. And the chain has a rainbow color. So it goes across the rainbow spectrum. So the different colors are different positions in the same chain. This is a much larger chain than that chain, right? So, and then this is what the collapsed coil looks like. And he says, you know, it's surprising it's a sphere, right? And it's got a lot of loops at the surface. If you look inside of it, there's like every neighbor is next to something far away from itself. Right, so it's kind of an odd thing to see like this. This is from a computer simulation. So it's kind of semi-real, I guess. You'll see in the paper we're doing this week, that this isn't what they say. They say it's different than this. So what they do is they take that chain and they put a tether on it, so they can see as it unfolds, like how the units separate. You know, they get a measure of it. They don't get an image of it, but they get a force image of how this happens. And it doesn't end up with this model at all. It's a different model. So anyway, so this is another picture, like this is used for drug delivery and things. So that's a picture of like the size difference you might get. Tanaka is a Japanese guy, but he was a famous polymer scientist, and he did this gel expansion stuff with PennyTamp, polyanisopropyl acrylamide, which was like the main thing people are working with for drug delivery, because it's like 30C, it phase separates. All right, so anyway, so and then you can launch that by temperature, so you can cool it down or heat it up if it's an LCST, and you can get this separation. You can also, and you'll see in the paper, he does heating and he does put salt in to salt out the charges on it to get that to happen, coil collapse. And then presumably, I mean, if you're talking about DNA folding or RNA or protein folding, then a biochemical, this is also Tanaka, so I don't know about electric field and I don't know what molecules means. Basically the solvent, changes solvent would change the thermodynamic conditions and thing. And light, I mean, the Japanese have done these things. There's papers on that, like how you have a gel changing. So anyway, the theory of it is like this. This guy doesn't stay hidden. Anyway, so we had, this is a Flory-Krigbaum equation. So we got, this is the ideal for the Helmholtz free energy. And then this is the excluded volume, including the one over, so this is B and then 1 over A over T, minus A over T. And A is an attractive potential, allows phase separation. And B enhances, it's excluded volume, so it enhances the things being apart. Right. So he's saying this is an enthalpic term. That's an entropic term, so it just looks like an expression for the free energy. Or this is the internal energy if it's Helmholtz. If it's Gibbs, that's an enthalpy. If it's Helmholtz, that's the internal energy. Right. So then he takes this and he rewrites it in terms of his alpha, which is a little bit different than the Fourier alpha. And he gets this. Then instead of talking about derivatives of the free energy with respect to R, he does derivatives of free energy with respect to alpha. When he does that, he immediately gets this answer. So if you do that, you'll find out that this zooms right into this 1/5 z to the 1/2. So that's z to the 1/10. And alpha is R by R naught, and R naught is z. So 1/10 minus, so 2/5 minus 5/5 gives you 3/5. That gives you the 3/5 law. It's actually, this is like a 3-step thing that does the entire Flory-Krigbaum. Actually, this thing is kind of interesting in and of itself that he could do that. And he doesn't seem to use that approximation, the thing about dropping terms and things. And yet he gets exactly the 3/5 law, which we know isn't right. Like the 3/5 isn't exactly right. That's 1.67. The actual answer is 1.72. So something weird about this, but I mean, he does, this is actually the whole Flory-Krigbaum in one step, you know. So it's kind of interesting he can do that. So there's some merit in this alpha thing, I guess. Anyway, so what do you do when the thing, so when the coil collapses, so it's dilute, so that the Mur units are far away from each other. And then even when it's in a theta condition, they're pretty far from each other. So you can ignore the higher order B, the second viral coefficient, and the third would be for higher concentration. So here, you need the third viral coefficient. Like you need to think about C. So you have B2 and then B3. So he calls it B and C. He uses his own nomenclature. So he's got B as this, and he's going to add in this C term to deal with when things get crowded, right? So this is the idea of B and C. So B, he says this, B is positive. So B positive means A is negative. A is an attractive potential, so A negative is a repulsive potential, right? So if you have a negative chi, it means you're driving to miscibility. So if B is positive, it's driving towards miscibility. That's the idea. And then he says C is negative. Nobody knows anything about C. Like there's no chi expression for C. It's just some number, right? So he's just saying it's negative. So it favors coil collapse. So three interaction term favors collapse. This one favors miscibility. They're competing with each other, right? So you're going to get a balance between those during the coil collapse. So what you want to get out of this is that when a protein folds, when DNA folds, it happens like boom, it happens. But when a polymer folds, it happens in a sequence of events. So when you get if you have like a phase transition from vapor to liquid, there's a big volume change in volume on cooling or whatever at the transition, right? So that's a first order transition because there's a big change in volume, delta V of the transition. And the same thing, like there's an enthalpy associated with it, right? It's a delta H. But if you go through like the glass transition, like in the rubber balls, there's no jump. Like it's the same stuff above and below. If you take a X-ray diffraction of it, it looks exactly the same as a glass or as a liquid. The only thing is it's kind of stuck, right? So it gets stuck. So it's not there's features of it that because it's stuck, it's got a different thermal expansion coefficient. So the derivative, the volume with respect to temperature changes. The slope of the curve of volume versus T changes, but there's no jump in volume. It's the same stuff above and below. It's just not expanding as fast. that's a second order transition. This is a derivative that gives you the so first order is biology and second order is polymers, synthetic polymers. So you want to know, you want to have a theory that can do both. If you can do that, then you've hit the jackpot, right? So that's the idea. He wants to get out of this first order and second order, and why you get the two. Why are they different? Right? So there's a lot. There's kind of a lot of little nuances to this thing. Anyway, so this is the model that he chooses. So this isn't something that came out of the blue. Okay, so later on, we're going to talk about what happens when you go through this. Let's see. So we'll talk about like what happens when you go through this. So structurally, like what happens. So we know that Foy-Krigbaum can make that black curve and fit the data, and we can get the chi parameter to judge to get that curve exactly, right? So, but like what actually is happening to the chain, because you have over here it's a good solvent and here it's a theta. So there's a difference between the two places, but yet there's a gradual change, not a discrete change, right? So the way to deal with that, and its evidence has come from neutron scattering to talk about that, and I'll talk about it later, is that you say thermally the thing collapses into a theta state. So you have the chain. It's like you take a piece of plastic and you heat it up with a flame. It kind of crinkles locally, and the size of it will shrink. So it's dense in the middle, and then the whole thing shrinks. But the overall piece of plastic still has this like random crumpled shape, right? So that's the idea here. As you drop the temperature, it like shrinks in the middle. So it goes to theta in little blobs, they call it. So it's a chain of blobs. And those blobs, as you go cooler, get larger and eat up more of the chain. The blobs are Gaussian and the chain's random walk. So you do get a transition from Gaussian to random walk, but it's this gradual transition because it's got this second size scale in the middle that's deciding what the overall size is, right? So that's the idea. That was around. There's also one for concentration. So we'll talk about those after. And there's also one if you like pull on the chain. There's like at least 3 kinds of blobs already. That's basically describing how things structurally change through these transitions, right? So it's because the thing covers like 4 orders of size. If you fully extend the chain, it's a micron, and the chain in the collapse state is going to be like nanometers. Right? So because you have 4 orders of size to play with, when you go through thermal transitions, it can make a new structure in the middle that accommodates it. So that's kind of how these macro molecular systems work in general. So you're always kind of looking for a new size like that, and he comes up with this collapsed blob. So he's looking for 3D, like the blob is going to be 3D. So he's got these little 3D blobs, and then he's got a chain. It's at the theta state. So it's at the theta state, and you cool it down more, it's still going to be theta state, just like this is expanded coil, and it's expanded coil right up until it gets to theta state. This is going to be theta state right up until it gets to collapsed. So the overall thing is theta state. The thing here is 3D. So it can be 3D and theta at the same time because it's got a new size scale that it introduces. So Grossberg, he was just BSing on this. He didn't have any evidence for this when he proposed this model, but you'll see in that paper that they show exact evidence for this. In fact, they show AFM micrographs showing the blobs. Yeah, so they kind of are on firmer grounding now than they were at the time when he proposed this whole thing. So anyway, so this is the idea, like those blobs grow, the 3D part grows and grows until the whole thing's 3D, and then finally end up with a sphere, right? Which I showed you a picture of, like the simulations could show a sphere, an actual sphere. So he shows it like a sphere here. The Chinese guy is going to say, no, it's not a sphere at all. It's like some other kind of thing. So they call it stacked. They say these blobs stacked in the paper. Anyway, so that's the idea. So then you can start just doing some scaling arguments for this. Like there's G star units in one of these 3D blobs. Then you can say the number of blobs is the total, like the weight divided by G star. And then if it's Gaussian, it's going to be Gaussian. R squared goes with N, NL squared. So R squared is going to go with the number of blobs in the thing. And then you can just make a expression for what the size of the chain is going to be from that. Right. So you end up with this idea that if you do that, you'll end up with 1 over alpha squared for this kind of entropic part. So we already had this alpha squared term from Floyd-Krigbaum, right? The second term, it was our first term, but now it's second term. This alpha squared, so alpha is r, so that's r squared by nl squared, 3/2 r squared by nl squared. Right? Alpha is a ratio of the 2 r's. So this is just the term we had before. Then from this analysis of this blob thing, he gets this 1 over alpha squared thing. Right, and then you have this expression alpha squared plus alpha minus 2. And you also have, which would account for expansion, which is alpha squared, confinement, which is minus 2. They're backwards here. But so basically, you have confinement and expansion. When you get when the coil expands a lot, right? So alpha is big when an expanded coil, this term drops out, and you just have the Floyd-Krigbaum again, right? And if the coil collapses down, this term becomes big, and then kind of that dominates over that. Right. So you have two things. You have the other thing is that when you have if you do rho squared here, you end up with alpha 6 for the C term. Not sure that's here, but the C term ends up being alpha 6 here because of the cube. That's not exactly explained, but it's on top of this. He talks about the density he uses, he calls n. Like, it's unfortunate some of the terms, the symbols he uses, but instead of using rho, he uses n. So n cubed is the density cubed. So that's a volume fraction cubed times c. And if you convert volume fraction cubed into alpha, so you have z cubed by r cubed, that's a volume fraction cubed. Then r cubed gives you alpha to the 6, because alpha's alpha is proportional to r. Somehow it works out to alpha to the 6, because z gives you r squared or something. Somehow it works out to alpha to the 6. So you have the first the second real coefficient, which is the thing we already had, which you wrote as alpha cubed. The third is this alpha 6 thing. Then you have this term for the ideal behavior of the thing. So you just have 4 terms instead of 3. And then you do the same thing. You do the derivative of this free energy with respect to alpha, set it to 0, and then solve for the coil expansion of the thing, or R. But alpha is the ratio of R's. So you can see, like, if it expands and the 6th term drops out, the 3rd is there. If it expands, the minus 2 term drops out, the 2nd is there. So you have Floyd-Krigbaum in the case of expansion. In the case of contraction, you have this kind of more complicated thing that involves 2 terms, B and C, the second real coefficient and third. Right. So you have to kind of map this out. That's kind of how this works. So he maps it out in terms of x, in terms of these 2 parameters, x and y. X is a function of B and y is a function of C. So this is the definition of x and y. So they're functions of B and C. And then you can rewrite this. This is expression, the Floyd-Krigbaum, this is the expression he gets out of that in terms of x and y, out of this equation by taking the derivative with respect to alpha. And then from that you can get an expression for R in terms of the C, which is in terms of C and B. And the Z is 1/3 from that. So it tells you that the coil size is going to be 1/3, means it's 3-dimensional. That part works out from his little thing. And then you get to this. So he gets plots of alpha versus the second real coefficient. So this second real coefficient's like chi, it's B over something over T, right? So basically this is like temperature and this is size. So it's almost like plotting volume versus temperature, like if you had a cubic equation of state. So cubic equation of state is like the van der Waals. That's van der Waals' house. It's got the cubic equation of state on the side of it. Anyway, so basically, when you're at high temperature, it behaves like an ideal gas. P goes as 1 over V. So PV is a constant. So P is 1 over V. That's this kind of swooping curve. As you get to lower temperature, the A term takes over, so you get attractive, you get phase separation. Then you get this weird little divot thing where you can have three solutions. You can have one here, one there, and one out here, like that, right? So you could have that pressure, you could have that pressure, you could have that pressure. This one doesn't exist. This one is low volume, so that's the liquid. This one's high volume, so that's the gas. If you have a gas and liquid in equilibrium with each other, you find the points that you want to pick out of. This is at one temperature. So you take one of these for one temperature, it's an isotherm. And then you pick the point you want by having these two areas equal to each other, which is called the Maxwell construction, to find the solution with the 2 points that are at equilibria. And then you take those 2 points and you plot them on a plot of pressure versus volume. You make those 2 points here, you do that for the others, and you get the phase diagram. Right, that's called the Maxwell construction. So he's got the same thing. That's the point. He's happy when he sees this. So he's got kind of a cubic equation of state. He knew enough to put it into a form that was a cubic equation of state, which basically all the equations of states you're going to use for gas liquid equilibrium are going to be cubic, and then it will have this behavior once you reach a critical point, below a critical point. And then he sees that too. So he has a region where you do a Maxwell construction, you get two equilibria, a big coil expansion and a small coil expansion. So it's separating between expanded coil and collapsed. Right. And he says that's a first order transition. It'll be a heated transition for that. So he draws a line between those. And if you're in this other region of temperature, you're going to get, or alpha, you're going to get this second order transition, which is a gradual change of coil expansion. So he says from this that he can get a first order or a second order, depending on where he is in the X plot, X alpha plot. That's kind of the idea of his thing here. So that's basically as much as you need to know about this, I think. It's got second order and first order in this thing. This is plots. So this is this penny pan, which is the same thing they're using in the paper this week. And this is the paper by, I don't know who these people are. Might also be a Chinese thing, but anyway, this group did a lot of work back in like 1998, 2008. So for a while, they were doing a lot of work on this. So just shows like, as you go across temperature, yes, you can get a transition. They use the Grossman theory to kind of model this change. And then they measure race of gyration and hydrodynamic radius both. And they take the ratio of the two. So when that ratio is 1.5, that's a theta coil. 1.6 is an expanded coil. 0.774 is a sphere. And they call 0.92 a draining sphere, whatever that is. So basically, they get to 0.992 at high temperatures. This is an LCST. Phase separates on heating, right? So I brought these things in. So these are the PV&E things. If you hold these in your hand, they'll go white. If they phase separate in the heat. Oh, you got it. All right, there's one. If you want to try it, there's a bunch of them here. Actually, which ones are better? You know which one's better because you tried it. He did this before, and I don't know. But anyway, you try to hold it. I don't know, just a couple. I don't know which one's better. The black one, actually, the blue ones might be better. Trying to do more than one, there's two more. So it's like really, these are just like when you buy this stuff. It comes with like a 50% water. I don't know, this one's too small, maybe. Oh, you didn't get one. This was the one. Maybe, I don't know. Anyway, it'll phase separate if it's warm enough. Basically like body temperature. You can see like your body could activate, if that was made into a gel, your body could release what was in it, you know. That's kind of the idea. So yeah, so it turns milky when it gets, that's called a cloud point, like phase separates. Yeah. So anyway, and that stuff, if you mix that PVME with let's see, this is 57. I have a picture of PVME in here somewhere. Back. right here. That's PVME. So it's like pretty simple polymer. It's a vinyl polymer.
Which slide is this?
This is slide 18.
No, I mean, I know there's one, there's two. Which number of this?
Oh, 2C,
Oh,
yeah,
2C.
yeah. Yeah, so this thing, you can also mix this with polystyrene. It mixes with polystyrene, it also has an LCSD. It's never been used for anything. But if you put an ethyl, instead of methyl, put 2 carbons here. That's a Post-it glue. That's the stuff that, like when you stick Post-its up. Which 3M made a ton of money on that. That was invented by like a secretary. Like a guy, there was a chemist who was messing around with these ethers. And he made the ethyl ether and he left it on the desk, and said like, I don't know, what are we going to do with this stuff? It stuck to things, And then the secretary like put it on paper and like started sticking things around the office, and then everybody wanted it. When that's where Post-its came from, basically invented by the secretary. So I'm not sure if you got a bonus for that or what, but it's like, anyway, so yeah, that's the stuff. So it's basically around room temperature, it's phase separating. And the PNEPM has almost the same behavior, right? So it's kind of the same behavior. So why is it that this is more popular than the PVME? So basically, this is the amide linkage. It's just like in a protein. So you have this double bond has a resonance structure. It can flip over to this bond. So it can flip back and forth. When you have a resonance structure, that makes it sheet. That makes it a solid sheet, it's planar. So in this case, you can think of that side group as like a card from a deck of cards. It's a solid sheet thing that's twirling around in space. If you look at proteins, so that's the same linkage, a carbonyl and an amide linkage, and this shows that it's a resonance structure with that double bond. So it makes this kind of solid thing. And this alpha carbon with the functional group on the side. It could be a sulfide for disulfide linkages or something. Right. So basically, this thing looks a lot like a protein. That's kind of why people like it. And it's got this LCST. You can see it's right. It's almost the same temperature, like 30C. You get in a phase transition. It's pretty easy to make this into a gel, into a network. So that's what they do, and make networks of it for drug delivery, basically, or whatever else they want to do with artificial muscle. This guy in this paper is talking about artificial muscle. If you take this and tether it somehow, when it collapses, it'll pull. It's an actuator. It's a thermal actuator. And he does it with salt too, right? So you can. Hey, so it's kind of an interesting polymer, I guess. It's PVME is kind of the same thing, but it's showing here like a picture of how that works. Anyway, so they get that it transitions from a 3D to a expanded coil, but they get this overshoot here, hysteresis they call it. So the hysteresis, they make a big deal about the hysteresis and what's going on in it. This is a first order transition, though, because it's almost first order, like it's just boom, it happens. You go through temperature, there'd be an enthalpy of that transition. In fact, when I was in grad school, a guy built a microcalorimeter and he measured the enthalpy of that transition. This guy, Howard Shield, and he later wrote a book on this stuff, about. So I guess, I don't know, it's kind of interesting to get a first order transition from a thing going through a coil transition like that. It's got ramifications for DNA and protein folding and things. So anyway, it's kind of interesting. So that's all I want to say really about. You don't need to be an expert at this thing. You just kind of need to know maybe that it exists. Like there is an explanation for why this thing happens. And it can describe first order and second order transitions. And it involves the third Viral coefficient, which you absolutely need to do this. And it also involves the idea that when you get denser, you have to worry about that the things form these blobs. Like the blob models in that first alpha term, right? The alpha to the -2 is the blob thing. And then C is just add in C. That's it. So So he used the blob model to get the alpha minus 2, and he gets a C. You need both of those to get this thing to work, to get this to be, that'd be a cubic equation. So you get that kind of Maxwell construction to get the phase behavior. All right. So anyway, that's that. We got a few minutes. So that's I wanted to get through that today, that's for sure. Did you know that one was going to phase separate, or like?
So, the last time I did, so the video is.
Yeah.
Because there was not enough heat.
Yeah.
So that's why I hold it for the long time.
Okay. Yeah, because you can. Yeah. I mean, you can see in that phase diagram that it's going to be, so it's going to depend a lot on the concentration that you picked out.
Yeah.
So, but this is like something like 5%, the peak of this. Yeah. So the dilute one should be better.
Okay.
The most dilute one you have should be the best one, but it doesn't seem to be the case. It seems to be you're like out here, because that one's kind of dilute looking, but at one point I had written the concentrations on these things, but it got wiped off. But anyway, if you have concentrated, it shouldn't really phase separate. You know, did you get that one to go, or?
Yeah.
Oh, well, they all phase separate, I guess. You know. Yeah. Anyone not get it to go? Oh, okay. Well, maybe you're somewhere out here. It's like, that's why it's not going to be just one temperature that works.
So apart from temperature, what are the other factors that is affecting this coil or this separation?
Well, I mean, this one, people don't talk about using salt here, even though it is like it's like a hydrogen bonding effect, right? Well, the water is organizing around it, and that'll have a big effect. Like, so maybe if you put salt into it, it would change it. And if you put, instead of water, if you put like ethanol, you know, then the miscibility drops like crazy. So, so you can change the solvent, you can put salt in. All these usually have some kind of ionic thing going on to make them mix. Because a polymer normally won't mix with anything, you know. Like to do GPC and polyethylene. To do that, they have to heat it up to like 100°C, and then they use dichlorobenzene for the solvent and the GPC. So it's hard, and if it cools down, then the whole machine's destroyed, you know, because it solidifies into the gel thing. They have tubes with gel where they run the polymer through it to get the molecular weight. So at high pressure. I don't know, that's kind of it, I guess. I mean, you can change the structure of in that paper, they changed the structure of the polymer. The molecular weight changes it. So the higher molecular weight phase separates earlier. We kind of saw that already. I don't know what else. Like these two, you know, the phase separation point's different for these two. They say that what they're looking at is that they say in this paper is they don't have hydrogen bonding here, and they do have hydrogen bonding here. There's still hydrogen bonding with the carbonyl, but not the amine. So you can see, like, if you have two protein chains next to each other, right? So the carbonyl hydrogen bonds with the amine. So if you have the other one lined up so that amine's here, then those two are going to form a sheet. That's why when you whip the egg, you're going to get the thing that's stiff. That's all beta sheet. So a natural thing, if you throw a nuclear bomb into a protein, you're going to get beta sheets out of it. You know, because they're going to just line up. They're going to just stack up that way, and it's going to be a 2D stack because these are all sheets. And if they stack that way, the hydrogen bond is just another sheet. So it's going to be sheet, like straight off, and that's going to form a beta sheet. You know, to get the helix, you have to do something else. Like you have to have these side groups interfere with it to get a twist of this thing. So anyway, so also it's going to be like water is going to be stuck to these things all over it, like amines and the carbonyl is going to have water stuck to them, and it's not going to be just one. There might be a bunch of waters hooked there. So basically, the thermodynamics of these things is going to be almost governed by this entropy of the water. You're fixing the water on it now. So if you fold this up, you're releasing a lot of water, you're increasing the entropy like mad. So folding might be favorable. If the chain's alone, it's holding a lot of water in place. And then once it folds, those hydrogen bonding sites aren't accessible anymore. The water's released, that's an entropy rise. And then that free energy goes down like mad, because it's the number of water is huge. So that kind of thing, like you completely overlook that if it's a synthetic polymer, you'd never think about that. That kind of entropic thing can be governing everything. But anyway, so it's that business. And we already, then this section kind of just jumps into rates of gyration and goes into scattering stuff. I can kind of start that, I guess. We get 10 minutes maybe. We already did the rates of gyration. That was in the last homework, right? So hopefully you kind of know what that is. So to measure that, you can figure out that it's this. If you calculate it for a polymer coil, you get this, that the rates of gyration squared is NL squared divided by 6. So they're directly proportional if it's a Gaussian chain. Right, but there's only certain cases, like if you have a sphere, so you have like 4/3 pi r cubed 4 pi squared. So if you have, if you want to, you'd want to integrate this surface area for sphere. So that would give you like the density at a position r, right? So you integrate that, and then you're going to integrate that same thing, 4 pi r squared dr, and if you want the rates of gyration, multiply by r squared and integrate that. Right, and that would give you Rg, because this is like the density function for the sphere. It's like spherical shells. Right, so this gives you R4. So the 4 pi cancels out. You have integral R4 over integral R2, right, which gives you R5 and then R3. The prefactor ends up being 3/5. Right, so you have R squared sphere, 3/5 is Rg. That's where he gets his Rg squared. So that's where he gets that number. He says this number should be whatever. That would be 0.6 R sphere squared equals Rg squared. So is that what it says here? Sphere should be, so RH, the hydrodynamic radius is, if it's a spherical radius, the equivalent spherical radius. If it is a sphere, RH is the radius of the sphere, right? So, RH by Rg by RH would be the square root of that thing. So square root of 3/5, square root of, so R by RH by Rg would be square root of 0.6, which I guess gives you 0.774 if you do it. Right, the ratio should be 3/5 for the squares, and then square root gives you that. So you can calculate for things like what Rg is, like simple objects. There's a table here somewhere. Here. So this is from some book, but basically the 3/5 of the sphere, circle shell. So if it's simple objects, you can just calculate it. Like cylinders, and then the polymer coil, you can calculate it, like the Gaussian polymer coil. So the Gaussian polymer coil, you take it, like the density function for a sphere is the surface, like 4 pi r squared dr, right? For a Gaussian coil, you take the positions of so you find the center of mass, find the position. That will be 1. Del means it's 1 if that thing's 0. So when you find the position and matches up with this difference, then that gives you that. So you plug in the NL squared for this thing, and you end up with basically this mess. So plug it, squared for the differences in positions. It's a double sum where N and M both change on the coil because you're doing all the different positions. And then that thing will end up being a power series, and the power series, this power series you can use to kind of solve that, and you'll end up finding that RG squared for the coil is that 1/6 power that we had before, that we did already. I guess I do that twice. So that kind of argument, like plugging in the NL squared, then doing this power series, so you can break down what it is. This kind of thing is like a matrix. You always end up with a double sum. So it's like the N and the M parameters are double matrix, and like we did with the Polymer isomeric state model thing to get the step length. It was a double sum also, except here it was a cosine of an angle you were summing, and here it's just the distance. So you always end up with this double sum in a matrix when you mess around with polymers. So what do I want to show you? So basically the way to measure this is with a scattering. I mean, that's the normal way to get the Ray's gyration. Oh, sorry. That would have been nice to know before. All right. Yeah, sorry about that. What I was showing this table of all the values, like here's the 3/5 value. Then you can do it for circle shell, ellipse. These are tabulated. You can just find. And they were calculated the same way as a sphere, like just a little bit more complicated integral thing. Anyway, so the way to measure this is with scattering. So this is a sketch of what a neutron scattering would look like and what the data would look like. So that's the intensity that you measure. Like in a diffraction measurement, you pick up the intensity, and this is kind of the reduced angle, right? So this is 4 pi over lambda sine theta, sine of the angle, by 2. So this Q factors, if you do Bragg's law, 1 over sine of the angle is the so here. So Bragg's law is that the size you get is going to be lambda by 2 sine theta. And your measurement as you shoot a beam comes out, and in that case you're talking about 2 theta here. And you measure the intensity here. So you take the smallest thing you can measure. So sine could go to 1. And then the smallest thing you can measure is lambda by 2. Because you're measuring the amplitude. So you're measuring the intensity. The amplitude goes like that. That's lambda. And then if you square, the intensity is going to be the amplitude squared. So the thing you're looking at is kind of like that. Right? And so basically half of the lambda is kind of what you can look at. So lambda by 2, and then as you go to smaller angles, you look at bigger things. So sine, when theta is small, then sine theta is the same thing as theta. So basically this is kind of like 1 over the angle. And Q equals 4 pi over lambda sine of theta. So basically Q is 2 pi over the d spacing. If you put this into that, you'll find out that Q is 1 over the d spacing. Right. So if you look at low Q, you're looking at large size. It's the inverse thing going on. Right. So anyway, so yeah, we got intensity, which is like the kind of proportional to the mass of the thing, and Q is inverse size. So the mass goes with the size to the fractal dimension. Then the slope is, if it's a log-log plot, the slope's the fractal dimension. That's 2 for the polymer coil. Until you get to the point where this thing starts to look like just a splot somewhere. So at some point, it doesn't look like. So if you zoom in on it, so you go to higher Q, you zoom it in, then it's self-similar. Like the smaller you get, it's still power 2, still Gaussian, until you get to the persistence where we go to 1. You zoom out, at some point you just see the whole thing as a single blob, like floating around. It's just a spot. So this is going to reflect the mass of that number of electrons in it, which is proportional to the mass. And it's also going to be reflecting the concentration of it. So you have the concentration times the number of electrons squared gives you this intensity because it's amplitude squared. So you end up with a square of the number inside the thing and then the concentration. Anyway, so that's this prefactor thing, the square of the number of electrons times the number of things, the concentration, times the Compton electron scattering factor. It's X-rays. And then this thing is a Gaussian. So if you look at it, this is say this is X. So it's X squared. So you'd have X squared divided by 2 sigma squared would be a Gaussian. This is inverse size. So 3 over RG squared is 2 sigma squared, and this is a Gaussian function, which is a bell-shaped curve about 0. Right? That's just saying, like, I shoot a beam of light through something, and what comes out is going to be a Gaussian. It's going to spread it out. Not very deep thought. It's basically just like the deeper thought is that the sigma, the standard deviation of that Gaussian, is the size of the thing that I'm shooting the light at. That's a little odd, right? But so 1 over the size of the thing I'm shooting the light at is the standard deviation of the Gaussian. If you plot a Gaussian in a log-log plot, it looks like this knee thing. That's a characteristic of a knee. So if you have this, like, one feature of it is there's no, so this is what the thing is. So you see, like, what it is, you have to zoom in to see what it is. You can't see it if you're a mile away from it, you just see a spot, and maybe you know the density of it. Like, what's the mass of it, right? So, but as you zoom in, you can see what it is. So this curve has no information about what it is. Like this Gunnier's law tells you that R raised to gyration tells you nothing about what it is. What it is comes out in the finer detail at the decades lower in intensity and at higher angle. That's where you get to what it is. What it is in this case is like is this random walk. In a lot of cases, what it is just a surface. You just get surface scattering where you get so small. Because I'll finish here. So when you get to so small, you think about it. So you have your thing, right? And you get to sizes like that. Well, if I have this and that, if I go half the size, I get total destructive interference. Like I get out of phase, 90-degree out of phase wave from that. So if I'm inside of something, there's always something halfway that kills any intensity I would get. I get intensity from those 2 points, but I also get these 2, which would be out of phase by 90 degrees. So the only possibility if you have a solid 3D object is to get like 2 points near the surface where you talk about like what's in the surface of this thing. Then there isn't a thing in between those. So you only get intensity from the surface when you get to a 3D object that's at high angle. So basically you can get the surface to volume ratio from that part, from the high Q part when you get to solid objects. Otherwise, if it has structure like this, then you'll see what the structure is. Right, so I don't know, I'll start there next time. I already go over. So I was trying to fill up the time, but I took too much. So anyway. So I want to click there. I'll go over that other paper next time on Friday. Any questions or anything? But I went through a bunch of stuff. So basically just the coil collapse thing is the important part here today. Guys are there.